we're going to pick up our discussion on radioactive decay by looking at the graphs and equations, or actually, we already have the equations. We're going to look at an important aspect of radioactive decay, and that's called half-life. We're going to relate it to the decay constant, talk about some important radioisotopes, and do an example problem, and then lastly finish off with this concept of quantum tunneling. Okay, so I'm assuming you've all heard of half-life before associated with radioactivity. And it's a time. We give it a special symbol, tau half. And it's simply the time it takes for half of the original parent nucleus sample. Okay, so we have to have a sample. It's not just one nucleus, but it is, we have generally a large sample that have decayed. And with that, we can take our equation for any radioactive decay and relate the half-life to the decay constant. We want to see that they're both properties of the material. Even though half-life is a time, and time changes with, as time changes, you get less and less of a particular parent nucleus. But we're going to see half-life is a given for a sample, regardless of how many nuclei you start with. So what we can start with is, of course, that our equation, the number of nuclei we have left at any given time is equal to what we started with, e to the decay constant multiplied by the amount of time. So when we're talking about half-life, the definition of half-life, when you have half the original sample, what that means is tau half isn't equal, but it corresponds to when n over n naught, your ratio of what you have to what you started with, is equal to 1/2. So we can use that then solve for what time, or how lambda, relates to half-life. So in this equation, the n over n naught, I'm just going to move to the left side, that becomes 1/2, and I've got e to the negative lambda. And I'm going to, instead of put t in there, I'm going to put tau half, because we want that specific time. What does that relate to? So to find what lambda and t are, I'm going to take the natural log of both sides. So if I take the natural log of 1/2, I'll let you work it out for yourself using log identities, but that's essentially the negative natural log of 2. Okay, so again, the natural log of positive half is the same as negative log of net 2, and that's simply going to equal negative lambda tau half. All right, so the negatives cancel. That's good because we want a positive value. And if I go over here, we see that half-life, okay, is simply equal to the natural log of 2 all over lambda. Or we could flip that around and say lambda is the natural log of 2 over the half-life. So we see that these two are directly related to each other. The quicker the decay constant, or the bigger lambda is, which generally means we have a very active material, it's a short half-life, we see that inverse relationship. So if we go to our curve, our exponential curve, right? So this is a generic e to the negative lambda t curve. Okay, then we see that if we look at half-life, so if I start with 100% of a sample and I go down half of it, I go over and I get a particular time. So that's tau half, which is labeled right here. And then if I go to half of my half, the quarter, I see that this time interval here is the same as that, which is the same as this, which is the same as that. So we see that with the DICE lab, if we haven't done it already. But again, that shows us that even though the amount of something changes with time, it drops exponentially, the amount of time to have each sample is always going to be the same. And the interesting thing about this curve is I can start anywhere on here. In other words, if I start, let's say, right here, and I drop down to roughly half, okay, I'm estimating now, and I go over the amount of time from here to here. In other words, look at this interval, I'll see it's the same as this interval. So it doesn't matter where you start on a curve, you should always get the same half-life. All right. So, what I want to say about this. The percent remaining, something we can also look at, percent remaining after a time, is equal to, related to the half-life. It's equal to 1 over 2 to the n, where n is the number of half-lives. Or half-lives, I'm not sure what that says. Okay, so if I ask you what percent do we have remaining after 1 half-life, that's 50%. If I have to ask after 2 half-lives, 25%, or 1 over 2 squared. So that's a convenient way of looking at half-life. Okay, where again, we can calculate n based on that definition I just put above as whatever time divided by the half-life. Okay, so that's sometimes a convenient thing to use. Alrighty, so let's look at some important half-lives, things that, especially as an IB diploma student, you need to be aware of. You don't have to have everything memorized, but there's certain ones that come up a lot that it's worth knowing, especially carbon-14, especially uranium-238, to a lesser extent polonium, and tritium is also important. So carbon-14, I think we've all heard of before. We've heard of carbon dating. And the reason carbon dating is so useful is in part because its half-life is on the order of thousands to tens of thousands of years. And so if you want to understand the age of something that was once alive, or let's say very common, we're looking at Paleolithic human societies or just people who are living and they have burned wood, if you find some of that charcoal that's left over, you can date it by using carbon-14 dating. So it is very important for dating organic material. You can't really use it to date rocks and that, because rocks are generally hundreds of thousands, millions to billions of years old, and with a half-life of only a half of 10,000, you're going to have very little sample left. The idea behind carbon-14 dating is this: when something is alive, it doesn't matter what it is, they always have a certain amount of natural carbon-14 in there, all the atoms that make up their organic structure. So that ratio to carbon-14 to carbon-12, which is the stable isotope, might be, let's say, 1%. But as long as something is alive, that ratio stays constant. Even though the carbon-14 is decaying, it will be replenished through the carbon cycle. As soon as something dies, that replenishment stops, and then that carbon-14, whatever was in there, is going to decay. And if you look at the percent that's left in your sample versus what we expected to be when it was alive, then we can get a good idea of how old it is. I'm going to come back to tritium. Uranium-238 has a really, really large half-life, 4 billion years. So what can we use that? That's dating the age of the Earth / rocks. And so our first really good estimate of the age of the Earth came from uranium-238 dating. And it's a really useful technique because that half-life is independent of the environment, independent of how much you have of uranium-238. And what you do is if you look at a sample that has uranium ore in it, and you look at the ratio of uranium to lead, because ultimately uranium will stabilize to lead, you can get a good idea of date. Plutonium is important because it is a huge issue with radioactive waste disposal from nuclear power plants, even from bomb makings. Okay, disposal or storage. So that's a major issue. Because its half-life is on the order of 22,000 years, it's going to stay active, radioactive, for many, 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 many generations. And so you have to store it away so people don't get exposed to it. And we're still working on that, what the best way to do that is. Tritium is important for fusion. We mentioned that a while ago. And because it has a very short half-life, you can't store it. So whatever natural tritium might be created, and remember it's a hydrogen isotope, you can't store it. So we have to create it in a facility. And there's not many facilities around the world that create tritium. Fortunately for fusion reactions, you don't need a whole lot of it. So let's do a quick little problem based on this. So based on the graph below, so this one, how much of a 0.512 kilogram radioactive sample will be left after 12 days? And expressed as a ratio of, or expressed as a percentage and as a mass. So in order to figure out how much is going to be left after 12 days, we could try to use the e to the negative lambda t equation, but we don't know what lambda is. So if we go to the graph, we're going to use the idea of half-life. So if I start with 80 counts per second, so this is activity right here, so it's not n, but activity follows the same idea. And I go down to 40 where it's a half-life, I go over and I see that tau half is 2 days. Okay, so now that I see that tau half, so I'm going to go up here, tau half is 2 days, I ask myself how many half-lives there are then. Well, we see that it's 6 days, so n in this equation up here is simply going to be 12 days divided by the amount of time for one half-life, so that's six half-lives. So I can say the percent left, and there's other ways of doing this, but this is the most straightforward. The percent that's left is equal to 1 over 2 to the 6th. because for each half-life we lose half. So 2 to the 6th is 0.015, which is equivalent to 1.5%. Okay, so very little of it's left. And so my mass that's left over is going to be 0.015 of the original mass, which is 0.512 kilograms. And so we're going to have about 8 grams left. Okay, so just look that over. I mean, I know I make it seem pretty simple and straightforward, but you got to work your head around how you would take this graph and go from there. Okay, so the next question is, what is the activity after 2.5 half-lives? Okay, so activity is A. Well, again, we can use the graph, we can do it graphically. So here's 1 half-life, 2 half-lives, and then 2.5 half-lives would be 5 days. I can go up, read the graph, and so I can get a approximation. So if I do it like that, okay, I see that my 2.5 half-lives is, well, hard to tell, but it looks like it's halfway between 10 and 15. So from the graph, I'm going to show you different methods. From the graph, it's about 15 days. The other way we could do it is we can say that the activity is equal to our original activity times 1 over 2 to the 2.5, okay, because it's 2.5 half-lives. So that's 80 was our original activity, times 1 over, that ratio is 0.177. So if I multiply them, I get 14.1, and I really should put counts per second or Becker, because that's the units for activity. So that's another way you could do it. I could also say, yeah, I already did it from the graph. We got about 15. So they match fairly well. And then D, what is the percent of original decay rate is the sample after 4 days? Oh, wait, excuse me. What is the value of the decay constant? Excuse me, I skipped one. Looked right over that. Let me just extend this, maybe. Okay, so just a reminder, we can relate decay constant to the half-life. So that's going to be the natural log of 2 over the half-life. And so you put in numbers. It's 0.35, and you can make sure you get the right units. It's per second. And then what percent is left after 4 days? That's really pretty much the same as the one part C. So the percent is going to be 1 over 2 squared, because 4 days is 2 half-lives. Okay, so that's simply 1/4 or 25%. All right. So lastly, how is it that different isotopes, radioisotopes, have different half-lives? And that really goes towards the decay constant. Why is it different? And so the best way to look at this is from an energy standpoint. We got to understand nucleus. You have 2 competing forces. You have the repulsive Coulomb force, which has a potential well associated that looks like this. And then you have the strong nuclear force, which is greater than that, which has a deeper well. The fact that it has a deeper well means that it's going to be the alpha particle, when it's inside a nucleus, is going to be in this part of the well. It's, in a sense, trapped. And in order to escape the nucleus, you think you need an input to get over the hump, right? So it's in this well, somewhere in this well, it has to get over this hump and then to escape. So normally in chemistry, if you have electrons in a similar situation, you have to give it a spark. You have to give it just a teeny bit of input of energy, and then it takes off spontaneously. With nuclear, we're told it's a purely random event. So there is not going to be an input of energy. So one way we can look at it is, how does an alpha particle get over this hump? Is that it can borrow energy in a sense of using Heisenberg's uncertainty principle. So that's one way of looking at it. In other words, if this represents an energy well right here, then there's a certain uncertainty in that energy for a given period of time. So in a sense, particles can borrow energy to get over that hump if it registers in a time that's really, really tiny. But the deeper the hole is, based on a radioactive isotope, the more energy it needs and the more unlikely it's going to happen. So essentially, different lambdas or half-lives come from the fact that the size of this well is different for different nucleotides. So the probability of it being able to give over the hump by borrowing the energy depends on how deep it is. Another way to look at it is just that if we represent a proton or a nucleon as a matter wave by Schrodinger's equation, then it will drop off exponentially. I'll talk about in class.